Heat and air conditioning losses in buildings and factories lead to large amounts of wasted energy. The largest cost-effective energy savings potential lies in residential and commercial buildings. Imagine a technology that creates a precise digital 3D model of heat distribution and heat flow that enables one to detect sources of wasted energy and to modify buildings to reach these savings. Recently, a lot of work has been done to capture and reconstruct the world around us. We can capture photos, point clouds, thermal images. But can we capture them all together? Let's take a laser scanner, a webcam, and a thermal camera, and mount them onto a mobile robot. The robot explores the environment and captures data. Each sensor perceives the world in its own local coordinate system. To join the perceived information, we need the specific parameters of these coordinate systems. The normal chessboard pattern is not reliably detectable in low-resolution thermal images. On the other hand, a board with clearly defined heat sources such as light bulbs shows up nicely in thermal images, thus enabling us to perform intrinsic calibration. To determine the position of the pattern in the laser scan, ransack is used to detect the plane through the board. Then a model plane is transformed into the center of the detected plane points and fitted to the data using an ICP algorithm. From the results, we know where the light bulbs are, and we can project the points onto a thermal image to retrieve the color information. The mapping of optical data is done in the same way. The sensor offset causes the sensors to see different parts of the world. An area that is visible for one sensor might be occluded for the other sensor, causing wrong correspondences and faults in the mapping phase. This impact is increased by the low resolution of the thermal camera, since each of the 120 by 160 pixels per image corresponds to many 3D laser scan points. Consequently, small calibration errors have a large impact on the results. To solve this problem, all points that are projected onto a pixel and its neighboring pixels are clustered, and only points belonging to the nearest largest cluster are colored. This also removes some correct color information, but the improvement prevails. In related approaches, expensive high-resolution cameras were used. Looking at our results shows that with decreasing resolution, quality decreases and error proneness increases. But in general, the results are adequate even at resolutions as low as 120 by 160 in an outdoor scene. Once we are able to correct the data, scans acquired at different positions were registered into one model using the SLAM60 software. The scene can be inspected in the viewer from 3D-TK to detect sources of wasted energy enhanced with either reflectance values, optical data, or thermal data. Switching between the thermal view and the optical view also has the further advantage that object detection algorithms from computer vision are applicable to identify heat sources. More information can be found on the following websites and the associated paper. This project was funded by the Sierra Net project, Thermal Mapper.